Hello there, students. So, you want to get to the other side of the river, but the current always pushes you downstream. We can fix that with an understanding of relative velocities covered in this video. To start talking about relative velocities, we need to label some reference frames. These reference frames are what we are measuring our velocities relative to, which is what we mean when we say relative velocities. For us, a reference frame will be a coordinate system, and we can attach it to anything we'd like. For example, we can attach a reference frame to this boat, this person, or the earth or ground, and sometimes even empty space. We label each reference frame with something reasonable, like B for boat, P for person, and G for ground. Most of the time, we instinctually measure with the ground as our reference frame. When we say a car has a speed of 70 kilometers per hour, that is relative to the ground beneath it. If instead we tried measuring the speed of that same car from the driver's perspective, well, the car isn't moving at all. It stays at the same location at all times relative to the driver, meaning a speed of 0 kilometers per hour relative to the driver. Hopefully this example shows you the importance of reference frames and relative velocities. Let's nail down some notation and see how this all works. In our previous videos, we've labeled positions, velocities, and accelerations with a single subscript, like v sub x, denoting the velocity in the x direction, or a sub y, denoting an acceleration in the y direction. For relative velocities and other relative quantities in general, we use two subscripts because we need to know two different things about the quantity. The first subscript is usually the object we are referring to, and the second subscript is usually the frame of reference with which the first subscript is being measured to. If we look at the car example again, we have the car, which we will label as C, and the ground labeled as G. So if we wanted to write out the velocity of the car, C, as seen in the reference frame of the ground, G, we would write V subscript CG. If we return to the problem of crossing a river with a flowing current, we'll see things get a little more complicated, but manageable with our new notation. First, we label some reference frames, G for ground, B for boat, W for water. When the boat tries to cross the river and is caught by the river current, the boat will be pushed downstream, like we saw in the intro. Standing on the ground, we measure the velocity of the water's current and label it V subscript WG. This means the velocity of the water W as measured from the ground G. If the boat tries to paddle directly across the river, it would have a velocity of V subscript BW as seen by the water's moving current. These are just two vectors, and if we wanted to know the actual velocity of the boat as seen from the ground, V subscript BG, we could just add these two vectors together, which would look like this. Graphically, the vector addition looks like this. The main thing to notice here are the subscripts in our notation. On the left, where we've added two velocities that have water W in their subscripts, the right side has no water subscript anymore. Also, the positions of the remaining subscripts are kept intact. So, where the boat B was the first subscript, meaning the leftmost, on the left side of the equation, it is still the first subscript on the right side of the equation. The same is true for the ground subscript G on the left and right side of the equations. Another example commonly used to teach relative velocities is using a passenger on a train. Let's use T for train, P for passenger or person, and G for ground. The train moves at a velocity relative to the ground of V subscript TG. If the person is moving inside the train, they will have a velocity relative to the train of V subscript PT. If instead the person in the train had been seated or standing still, they would have the exact same velocity as the train, as measured from the ground G. Since they are moving within the train, the person no longer appears to have the exact same velocity as the train relative to the ground. Instead, they are now moving at some other velocity, v subscript pg. This is the velocity of the moving person inside the train as measured from the ground. Learning from our previous example, from the boat on the river, we can figure out that this velocity, v subscript pg, is equal to the velocity of the train relative to the ground, v subscript tg, plus the velocity of the person relative to the train, v subscript pt. If the person inside the train were moving in the opposite direction than the train itself was moving, it's possible the person wouldn't appear to be moving at all from the perspective of the ground. This is what happens on, say, a treadmill. The treadmill belt is moving in one direction relative to the ground, and the person is moving in the opposite direction relative to the belt, canceling each other out as seen from the ground's perspective, making the person remain stationary. In the next video, we'll start attaching some numbers to these velocities to see how they might be useful in practice. Until then, thanks for watching and learning about physics. Leave a comment below if you found this useful, or leave a suggestion for what kind of physics content you'd like to see a video on.